Across the universe, there are structures so enormous they defy intuition. Stars swollen wider than orbits, black holes heavier than billions of suns, and cosmic clusters stretching farther than light can cross in a lifetime. These giants aren't exaggerations. They are real, measured objects that dwarf everything our minds evolved to understand. Tonight on Sleepy Traveler, we drift toward these colossal forms and trace how the universe builds such overwhelming scale, turning terror into quiet curiosity. If this soft journey feels right to you, a gentle like and a quiet subscribe help other travelers find their way here. Settle in now, and we'll step into the vastness together. Out in the dark, the universe is scattered with shapes so large they almost slip out of human imagination. There are stars that make our sun feel like a small lantern, planets swollen to impossible sizes, and black holes so heavy that whole swarms of stars drift in slow circles around them. In this quiet cosmic theater, these giants quietly stretch the limits of what we thought could exist. And if the idea of endless distances and towering things has ever made you feel a little uneasy, these immense wonders may send a soft shiver through the mind, even as you lie still. One of the strangest of these giants is a world called WASP 17b, a planet that behaves less like a solid globe and more like a swollen cloud. It is a gas giant, but not like the ones we know in our own solar system. Imagine a world almost twice the width of Jupiter, yet with only about half of Jupiter's mass. Huge, but surprisingly light, as if someone gently inflated it from within. Astronomers sometimes call it a puffy planet because its atmosphere billows far outward, giving it the look of a cosmic balloon drifting around its star. WASP 17b orbits a distant star in the constellation of Scorpius, around 1,300 light-years from Earth. It was first found by the Wide-Angle Search for Planets, a project that does not look for direct images of planets, but for tiny changes in starlight. When a planet passes in front of its star from our point of view, the star's brightness dips just a little, like a lamp briefly dimmed by a moth's wings. That gentle blink gave this strange world away. From the amount of light blocked, astronomers could tell that WASP 17b has a very large silhouette. But when they measured how strongly it tugs on its star, they found that its mass is far lower than such a big planet should have. It was as though a giant shadow crossed the star, yet the object casting it weighed only a fraction of what was expected. The simplest way to explain this is an extremely extended atmosphere, a deep, airy shell of gas surrounding a much smaller core, making the whole planet look larger than it really is inside. Normally, the stronger a planet's gravity, the more tightly it squeezes its own atmosphere. But WASP 17b lives so close to its star that it is bathed in fierce, constant light and heat. It completes an orbit in only a few Earth days, racing around in a tight, hot loop. All that radiation pours into its outer layers, warming them until they swell and thin like air inside a heated lantern. Temperatures in its atmosphere are estimated to reach well over 1,500 degrees Celsius, hot enough to melt many familiar metals into glowing liquid. This heat does more than puff the planet up. The star's light and wind slowly nibble at the planet's outermost gases, stripping them away into space. Over long stretches of time, WASP 17b may be gently losing part of its airy shell, its upper atmosphere trailing off like a faint, invisible mist. It is a giant, but in some ways a fragile one, slowly eroded by the very star that keeps it so bright and swollen. There is another oddity. Most planets circle their stars in the same direction that the stars spin, like dancers moving along with the turning of the room. WASP 17b does the opposite. It travels in what astronomers call a retrograde orbit, moving against the spin of its star. Imagine one lone dancer walking slowly upstream through a flowing crowd. Something dramatic must have happened in the planet's past to twist its path around like that. Perhaps it once passed close to another giant planet, and their shared gravity flung WASP-17b into a reversed orbit. Or perhaps the early, unsettled disk of gas and dust around the star tilted and tugged it into this strange motion. Astronomers are still exploring why WASP-17b is so inflated. One idea is that the intense radiation from the nearby star keeps pouring energy into the outer atmosphere, so the gas simply cannot settle down into a tighter shape. Another possibility is that the planet formed with more light gases, such as hydrogen and helium, and fewer heavy elements, making it airy from birth. On top of that, strong tidal forces from the star may be kneading the planet's interior, stirring it and adding heat from within. Fierce winds may circle the globe, redistributing that heat in fast, high currents. To learn what this world is really made of, scientists watch its star during each transit and study how the light changes. As the star's rays pass through the thin edge of the planet's atmosphere, certain colors are absorbed or scattered by specific atoms and molecules. These tiny changes act like fingerprints in the starlight. Early observations suggest that WASP-17b may be wrapped in hazes or clouds, layers that soften and tint the light. Each new piece of data reveals a little more about its chemistry and weather, and about how planets behave when they are pushed so close to their stars. When we compare it with Jupiter, the contrast is clear. Jupiter is also a gas giant, but it is far denser and more compact, with its mass drawn in under strong gravity. WASP-17b shows that gas giants can follow very different paths. Some live in cool, distant orbits and remain tightly bound. Others, like this puffy planet, are pulled close enough to their stars that they swell into great, airy spheres. Some exoplanets are hotter than anything we know at home, some are colder than we expected, and a few are so light and bloated that they almost seem to challenge the word planet. By studying them, astronomers refine their ideas about how planets form and how they change under extreme conditions. WASP-17b, one of the most extreme of these worlds, has become a gentle reminder that the universe is far more inventive than our first guesses. Far beyond this softly inflated planet, another kind of giant once announced itself in a single, brilliant event. In the late 1980s, a star in a nearby companion galaxy of the Milky Way exploded as a supernova, now known as SN 1987A. By cosmic standards, it was close, in a small galaxy called the Large Magellanic Cloud that orbits our own like a pale smudge in the southern sky. Because it was so near, and because modern instruments were already watching, SN 1987A became the first supernova to be followed step by step with great detail. Before this, most supernovae appeared as brief, distant flares, brightening and fading too far away for their inner workings to be traced. This one was bright enough for astronomers to watch its light evolve, to see the expanding shell of debris change over time. The star that died was a blue supergiant called Sandulik, 69-202, much hotter and more compact than the red supergiants that had long been considered the usual candidates for such explosions. For millions of years, that star had fused hydrogen into helium in its core, then moved on to heavier elements as it aged, building a layered interior. At last, the core ran out of fuel. Without the outward push of fusion, gravity took over, and the core collapsed inward in a sudden, catastrophic fall. In that brief moment, the core became incredibly dense, and a shock wave rebounded outward, tearing through the star's outer layers and flinging them into space. The energy released in those seconds outshone whole galaxies, lighting up the surrounding region. A quiet but crucial piece of evidence arrived not as light but as a rush of nearly invisible particles called neutrinos. These almost massless particles stream out in vast numbers when a massive star's core collapses. They rarely interact with matter, moving through entire planets as if they were not there. Yet, just before SN 1987A was widely seen in visible light, underground detectors on Earth registered a brief burst of neutrinos. It was like hearing a distant, muffled drumbeat before seeing the flash. This confirmed that neutrinos play a central role in core collapse, carrying away energy and helping the shock wave escape the dying star. The fact that the star was a blue supergiant forced astronomers to rethink their picture of how massive stars end their lives. Red supergiants, cool, swollen, and unstable, had seemed the natural precursors of core collapse supernovae. Now, with a hot, compact blue star providing the spectacle, models had to be adjusted. Perhaps some stars shift between these states. Perhaps strong winds, rotation, or the presence of a companion star strip away outer layers and change a star's appearance before it explodes. SN 1987A became a kind of living lesson on how complex stellar evolution can be. In the years that followed, telescopes kept returning to the fading remnant. As the expanding debris pushed into the surrounding gas, it glowed in many kinds of light, from visible to X-ray and radio. One of the most striking features appeared as a series of glowing rings encircling the explosion site, like delicate halos suspended in space. These rings are thought to be material that the star shed thousands of years before it died, perhaps through strong winds or interactions with a companion star. When the blast wave from the supernova reached these older shells, it heated them and made them shine, tracing the outline of the star's own history. As the debris continues to expand, it plows into the interstellar medium, heating that gas and shaping it. By watching this process, astronomers learn how supernova remnants grow, how they stir and enrich their neighborhoods, and how they spread heavy elements such as carbon, oxygen, and iron that later become part of new stars, planets, and maybe living beings. What looks at first like a sudden ending is also a beginning, scattering the ingredients for future worlds. Deep within the remnant, the collapsed core is thought to have become a neutron star, a city-sized sphere where matter is crushed to enormous density. Protons and electrons are squeezed together into neutrons, forming a single, dense fluid. For many years, scientists searched for evidence of this object inside SN 1987A. Recent observations hint at a hot, compact source of radiation hidden behind dust, a possible newborn neutron star still wrapped in its cocoon, slowly cooling and changing. Another quiet surprise came from the dust that formed as the debris cooled. At one time, supernovae were thought mainly to destroy dust grains, but SN 1987A showed that fresh dust can condense in the cooling material in large amounts. This suggested that such explosions are not only wrecking balls but also factories, helping to fill galaxies with the fine solid particles that later clump into comets, asteroids, and rocky planets. Because it was so close and so carefully observed, SN 1987A has become a benchmark. By comparing more distant supernovae to this event, astronomers refine their models of how stars collapse, how shock waves move, how neutrinos behave, and how remnants evolve over decades. Powerful observatories, including the James Webb Space Telescope, still watch its expanding fronts and glowing rings, drawing out new details from the same cosmic story. From that violent flash far away, we can drift back towards something nearer and more familiar: Jupiter, the great gas giant that rules the outer reaches of our own solar system. Jupiter is the largest planet we have, a vast world made mostly of hydrogen and helium, with no solid ground to stand on. As you move inward, the gas grows denser and stranger, pressed by gravity into deep, hidden layers. Its pull has helped shape the paths of comets and asteroids and guided the way our planetary family settled into place. Jupiter's scale is almost beyond ordinary sense. You could fit more than 1,000 Earth-sized worlds inside its volume. Its mass is hundreds of times that of Earth. Had it been many times more massive still, the pressure and temperature in its core might have been high enough to ignite nuclear fusion and turn it into a faint star. Instead, it rests just below that threshold, a planet that almost became something more, yet found its own way to be important. The other giant planets, Saturn, Uranus, and Neptune, have their own personalities, but Jupiter is the standard. When astronomers discover gas giants around distant stars, they often describe them in Jupiter units. This many times Jupiter's mass, that many times Jupiter's radius. Some of those exoplanets are hot Jupiters, similar in size but huddled close to their stars, baking in tight, short orbits. Others are super Jupiters, more massive and pressing against the upper limit of what we call a planet. In each case, Jupiter serves as the quiet reference, the familiar giant against which all the others are measured. Its own face is endlessly in motion. The thick atmosphere is wrapped in clouds of ammonia and water, stretched into broad bands that circle the planet. Strong winds race through these regions, drawing the clouds into pale zones and darker belts that run parallel to the equator. Powerful jet streams keep these bands moving in opposite directions, creating immense storms where they meet. The most famous of these tempests is the Great Red Spot, a swirling high-pressure storm that has been turning in the planet's clouds for centuries. It is so broad that an Earth-sized world could disappear inside it, a whole blue marble swallowed by a single curl of weather. For at least 200 years we have watched it, sketching it through old telescopes and photographing it with modern spacecraft. In recent decades, it has slowly shrunk, as if the storm is quietly tiring, but it remains one of Jupiter's defining marks, a red, oval eye in the bands, proof of how wild and long-lived its atmosphere can be. All around it, smaller tempests rise and fade, white ovals, brown barges, and countless storms form, merge, and dissolve, like whirlpools in a vast painted sea. By watching these patterns, scientists learn how winds, heat, and rotation dance together in a giant planet sky. Jupiter becomes a laboratory in motion, showing us how atmospheres behave when scale and energy are pushed far beyond anything we know on Earth. Beneath those swirling clouds, Jupiter hides a deep mystery. There is no firm ground where the clouds end and a surface begins. Instead, the gases grow thicker and hotter as you travel downward, gradually giving way to a strange interior. Under crushing pressures, hydrogen gas is squeezed so tightly that it shifts into an exotic state called metallic hydrogen. In this form, it is thought to flow like a liquid metal, able to carry electric currents. Those moving charges, in turn, help generate Jupiter's powerful magnetic field. That magnetic field is one of the strongest of any planet in the solar system. It stretches far into space, wrapping Jupiter in a huge invisible bubble and trapping high-energy particles. Around the planet, these particles form intense radiation belts, harsher than the regions around Earth. Any spacecraft that ventures too close must carry special shielding, like armor, to survive the bombardment of charged particles racing along the magnetic lines. Deep at the center, scientists think there is a compact core made of heavy elements, rock, metal, or a mixture wrapped in layers of metallic hydrogen and dense fluid. But the exact nature of this heart remains uncertain. Some models suggest that the core may be partly dissolved into the surrounding layers, blurring any clear boundary between solid and liquid. Others picture a more sharply defined, dense core hidden under thousands of kilometers of pressure. Understanding this hidden heart is key to understanding how Jupiter formed, and by extension, how gas giants are born around other stars. Jupiter's reach does not end with its clouds. Its gravity holds a whole miniature system of moons, at least 95 worlds that range from small, irregular chunks of ice and rock to large, complex bodies that rival planets. The four largest, called the Galilean moons Io, Europa, Ganymede, and Callisto, were first seen by Galileo Galilei in the early 1600s. Each carries its own quiet wonder. Io is the most volcanically active body we know, its surface constantly reshaped by eruptions that fling sulfur and lava into space. Europa is wrapped in a smooth shell of ice, scored by dark cracks. Beneath that shell, strong hints point to a deep ocean of liquid water, kept from freezing solid by the constant tug and flex of Jupiter's gravity. That hidden sea makes Europa one of the most promising places in the solar system to search for life beyond Earth. Ganymede, the largest moon of all, is bigger than Mercury and even has its own magnetic field, a sign of an active interior. Callisto, heavily cratered and ancient, preserves scars from the earliest days of the solar system, like an old, pitted memory, frozen in ice and rock. Jupiter itself has helped sculpt the solar system we live in. Its gravity has nudged and herded countless comets and asteroids, sometimes flinging dangerous objects away from the inner planets, sometimes redirecting them inward. Some ideas suggest that in the solar system's youth, Jupiter helped clear out much of the debris beyond Mars, preventing more massive planets from forming there. Other ideas suggest that its pull may have disrupted the birth of a super-Earth in the inner system, changing the final arrangement of worlds. In either case, this giant has quietly influenced the path of planetary evolution. Spacecraft have flown past Jupiter for decades, but NASA's Juno mission has given us some of the most intimate views. Skimming close above the cloud tops in a long, looping orbit, Juno has mapped the magnetic field, sampled the deep atmosphere, and photographed Jupiter's poles, revealing clusters of swirling cyclones arranged like flower petals around each pole. Future missions, especially those aimed at the icy moons, will continue to explore this giant world and the family of worlds it shelters, adding new pieces to the story of how such giants fit into the wider cosmic puzzle. From Jupiter, our thoughts drift naturally back to the star that makes all of this possible. The Sun is the warm heart of our solar system, a vast sphere of glowing plasma whose light and heat make Earth's gentle conditions possible. To our eyes, it seems steady, a familiar disk that rises and sets every day. But in truth, it is a restless, churning engine of nuclear fire. The Sun is far larger than our planet. Its diameter is roughly 109 times wider than Earth's, and more than 1 million Earths could fit inside its volume. Yet in the family of stars, it is only moderate in size. There are stars hundreds of times wider, and some so huge that they would engulf the orbits of planets entirely. For us, though, the Sun is the standard by which we measure others. It is classified as a G-type main sequence star, a kind of steady, middle-aged star with a long and stable life. At its core, the Sun is a nuclear furnace. There, at temperatures of around 15 million degrees Celsius, hydrogen nuclei are pressed together so violently that they fuse into helium. Each fusion reaction releases energy, and together they give the Sun its brilliance. The energy made in the core begins a long outward journey, bouncing from particle to particle in a dense region called the radiative zone, where photons are endlessly absorbed and re-emitted. It can take an almost unimaginable length of time for this energy to wander outward to the next layer. Eventually, it reaches the convective zone, where hot gas rises and cooler gas sinks, creating a slow, boiling motion, like water simmering in a pot. This churning helps carry energy upward to the visible surface. The photosphere, the layer we see from Earth, glows with a temperature of about 5,500 degrees Celsius, its surface modeled by tiny granules, where hot gas rises and cools. Above the photosphere lie the chromosphere and the corona, more tenuous layers of very hot plasma that extend far into space. The corona, in particular, is puzzling. It is far hotter than the surface below it, a fact that still challenges our understanding. During a total solar eclipse, when the moon blocks the bright disk, the corona appears as a pale, feathery halo around the darkened Sunday. From this outer region, streams of charged particles blow outward in all directions as the solar wind, a constant flow that washes over the planets and shapes their magnetic environments. Despite its reliable light, the Sun is not perfectly calm. It goes through cycles of activity lasting about 11 years, during which its magnetic field tangles and rearranges. Dark patches called sunspots appear on its surface, where magnetic fields are especially strong. Some sunspots grow larger than Earth itself. These active regions can spawn solar flares and coronal mass ejections, eruptions that throw bursts of energy and charged particles into space. When those particles reach Earth, they can disturb satellites and power systems, but they also paint the sky near the poles with shimmering curtains of color, the auroras, or northern and southern lights. The Sun's gravity holds the entire solar system together, keeping planets, moons, asteroids, and comets bound in their paths. Its light drives the water cycle on Earth, powers photosynthesis in plants, and provides the warmth needed for liquid water to exist on our surface. Without it, our world would be a frozen, airless rock drifting in darkness. And yet, for all its importance, the Sun is not eternal. By our estimates, the Sun is about 4.5 billion years old, roughly halfway through its stable life. It has enough hydrogen in its core to continue shining for around another 5 billion years. Eventually, that central fuel will run low. The core will contract and heat up, while the outer layers expand and cool. In this later phase, the Sun will swell into a red giant, so large that it may engulf Mercury, Venus, and possibly Earth. Its outer layers will then be gently blown away, forming a glowing shell of gas called a planetary nebula. At the center, all that will remain is a dense, hot remnant called a white dwarf, slowly fading over time. Although the Sun is not the largest star, it serves as a vital reference. Astronomers describe distant stars as larger or smaller, hotter or cooler than the Sunday. Red dwarfs are smaller and cooler, with dimmer, longer lives. Blue giants are more massive, hotter, and shorter-lived. Some red supergiants, such as the star Betelgeuse, are hundreds of times the Sun's size. Hypergiants like the star UY Scuti reach scales that are hard to truly imagine. By comparing them to our Sun, we can place them on a common scale and better understand the full range of stellar lives. Far beyond the calm distance where our gas giants circle, there are planets that live in far harsher conditions. One of the most dramatic is WASP 12b, a scorching hot Jupiter on the verge of being torn apart. WASP 12b is a gas giant that orbits so close to its star that the star's gravity is actively pulling the planet's outer layers away. The heat is so intense that it has altered the planet's very shape and structure. This world lies roughly 1,400 light-years from Earth in the constellation of Orion. It was discovered in the late 2000 single digits using the same transit method that revealed many other exoplanets. As WASP 12b passes in front of its star, the starlight dips by a noticeable amount, revealing a large planet in an extremely tight orbit. It takes only about 1.1 Earth days for the planet to complete a full circle around its star, which means it skims alarmingly close to the stellar surface. At such a distance, the planet is bathed in fierce radiation. Temperatures in its atmosphere are estimated to climb above 2,500 degrees Celsius. In that furnace, many molecules cannot remain intact. They are broken apart by the heat. The atmosphere swells and stretches, drawn toward the star by gravity. Instead of a neat, round shape, the planet is pulled into something more like a teardrop, its outer gases spilling toward the star. This process, called atmospheric escape, is steadily eroding WASP 12b, stripping away its mass and reshaping it in a way unlike anything seen in our own solar system. The tidal forces involved, the same basic kind of gravitational pull that raises ocean tides on Earth, are far stronger here. On Earth, tides gently lift and lower the seas. On WASP 12b, the star's gravity stretches the planet itself. Even among hot Jupiters, this world is extreme, pushed close to the edge of being ripped apart. Another startling trait is its darkness. Observations suggest that WASP 12b absorbs more than 90% of the light that falls on it, making it one of the darkest known planets. Most gas giants reflect at least some light, especially if they have bright cloud tops, but this planet's broiling atmosphere appears to trap most of the incoming light. The lack of reflective clouds, combined with heat-loving molecules that absorb rather than scatter starlight, may leave WASP 12b cloaked in a deep, light-eating gloom. The planet's future is grim on astronomical timescales. As it continues to lose mass to its star, it may shrink into a much smaller, denser world, or be destroyed entirely, its material spiraling into the star or spreading out in a thin ring. Events like this are rare, but they offer a precious chance to watch the final stages of a planet's life up close. By studying WASP 12b, Astronomers gain clues about what can happen to other planets that wander too close to their stars. Despite its dangerous orbit, WASP-12b has survived long enough for us to study how it is changing over time. This suggests that some planets can resist complete destruction longer than we might expect, even under extreme conditions. Its stretched shape, intense heat, and rapid loss of atmosphere make it an important example of how exoplanets can be altered by their environments. In our own solar system, gas giants live far from the sun, where temperatures are low enough for them to keep their thick envelopes of gas. WASP-12b shows that gas giants can also exist in regions where survival seems almost impossible, either by forming there or by migrating inward from cooler distances. Some theories propose that it may have started farther out and then slowly moved inward due to gravitational interactions with other planets or with the disk of gas and dust that once surrounded its star. Astronomers have detected elements such as hydrogen, helium, and carbon-bearing molecules in its atmosphere. The presence of carbon-rich compounds hints that its chemistry could differ from Jupiter's, which is richer in oxygen-bearing molecules. Future observations may reveal more details about the specific gases present, how they respond to heat and radiation, and how the atmosphere evolves as the planet continues to lose mass. While Earth orbits at a gentle distance that allows liquid water, familiar air, and stable conditions for life, many exoplanets exist in far more chaotic and hostile environments. By studying extreme cases like WASP-12b, scientists can better understand how planets change over time, how they interact with their stars, and what combinations of distance, heat, and composition might make a world habitable or uninhabitable. One of the worlds that quietly changed how we study the cosmos is HD 209458b, often nicknamed Osiris. It is a gas giant circling a sun-like star in the constellation Pegasus, about 159 light-years from where you are now. When it was announced in the year 1999, Osiris was not just another distant planet. It was the first exoplanet ever seen passing directly in front of its star, the first world to reveal itself through what we now call the transit method. Before Osiris, most planets around other stars had been found by watching their suns wobble, tugged gently by the invisible pull of orbiting worlds. That radial velocity method was powerful, but it mostly told us that something was there. We did not yet see the shapes of those planets, only their fingerprints in starlight. Osiris changed that as it slipped across the face of its star, the star dimmed by a tiny, regular amount. From that faint blink, astronomers could measure how large the planet must be. They found that Osiris is about 30% more massive than Jupiter, but even more swollen in size, puffed up by the heat of its nearby star. It races around that star in about 3.5 Earth days, in a tight orbit so close that one side always faces the light. Like a moon locked to its planet, Osiris is tidally locked, with one hemisphere in endless day and the other in everlasting night. The transit did not just outline the planet's size. As Osiris passed in front of its star, a thin rim of starlight filtered through the planet's upper atmosphere before reaching our telescopes. Different gases absorb different colors, so by examining exactly how the starlight changed, scientists could tease out what was floating in that alien sky. It was the first time we had ever read the atmosphere of a world so far away. In that faint spectrum, they found hints of water vapor and carbon-bearing molecules such as carbon monoxide and carbon dioxide, along with signs of oxygen locked inside those compounds. There were clues to high-altitude hazes or clouds, suggesting that the upper atmosphere is not calm, but shifting and layered. The picture that emerged was of a hot, windy world, shaped by intense starlight. Models suggest that in the upper layers, winds may scream around the planet at thousands of kilometers per hour. The day side bakes under constant glare, while the night side sits in deep shadow. High-speed winds rush from the bright hemisphere toward the dark, smearing heat around the globe and blurring the temperature contrast. Where Jupiter wears clear bands of clouds, Osiris seems wrapped in a softer, hazier cloak. Different temperatures, different chemistry, and a much harsher radiation environment have given it a personality all its own. Because Osiris was one of the first exoplanets studied in such detail, it became a quiet standard for comparison. Observations from the Hubble Space Telescope, the Spitzer Space Telescope, and later instruments have refined our picture of its atmosphere and structure. The methods tested on this one planet have since been applied to thousands of others. The transit technique has grown into one of the most fruitful ways of finding exoplanets, revealing worlds ranging from small rocky ones to giant, bloated spheres like Osiris. Perhaps most importantly, Osiris proved that we can study the air of distant planets, not just their orbits. That ability to read atmospheres light years away opens a path towards searching for life. On future worlds, astronomers will look for key gases such as oxygen and methane, or combinations that are hard to explain without biological processes. In that sense, Osiris is like an early stepping stone on a long and delicate path toward answering whether other skies might host living things. From this hot, wind-lashed planet, we can drift in our thoughts towards something far larger and more ancient, a dying star that has watched over human stories for countless nights. Betelgeuse, glowing reddish in the shoulder of Orion, is one of the most familiar stars in the sky. To the naked eye, it is just a bright point, but it is, in fact, a red supergiant star nearing the end of its life. Betelgeuse has swollen to a radius roughly 700 times that of the Sunday. If you placed it at the center of our solar system, its outer layers would stretch beyond the orbit of Mars. Yet those layers are incredibly thin. Instead of a sharp surface, Betelgeuse has a diffuse envelope, more like a drifting cloud of gas. Its density is low for a star, and its light flickers and shifts as those outer layers swell, cool, and contract. Its brightness is not steady. Over months and years, Betelgeuse slowly brightens and dims, the result of complex motions in its atmosphere and changes in temperature and density high above its core. In late 2019 and early 2020, the star experienced an especially dramatic dimming. Its light dropped to levels never recorded before, and for a moment the world wondered if we were watching the prelude to a supernova. Later observations gently corrected the story. The dimming was most likely caused by a massive cloud of dust that Betelgeuse had thrown off, drifting into the line between star and Earth and blocking some of its light. When that dust cooled and dispersed, the star's brightness returned to normal. It was not the final act, only a reminder that the star is restless and unstable. Inside, Betelgeuse has already burned through the hydrogen that once fueled its core. It is now fusing heavier elements in nested shells, trying to hold gravity at bay. Eventually, it will begin to build up iron in its core. Iron cannot release energy through fusion, so when enough iron accumulates, the delicate balance between outward pressure and inward pull will fail. The core will collapse in a fraction of a second, and the outer layers will be blasted into space in a brilliant supernova. When that happens, Betelgeuse will suddenly become as bright as a full moon, perhaps even visible in the daytime sky for weeks. Its outer layers will be cast off as a glowing cloud, while its core shrinks into a neutron star, or possibly a black hole if there is enough mass. Because Betelgeuse is relatively close, around 640 light-years away, its explosion will offer astronomers an extraordinary chance to watch a nearby stellar death unfold from the very beginning. Despite the drama of that future, there is no danger to Earth. At that distance, the deadly parts of the explosion will dissipate long before they could reach us. For us, Betelgeuse's supernova will be a show, not a threat, a rare chance to see one of nature's grandest events without harm. Around the star, infrared telescopes have revealed arcs and knots of gas and dust, material Betelgeuse has shed over thousands of years. These structures trace past eruptions and winds, a history written in glowing filaments. The star is also plowing through the galaxy at high speed, creating a bow-shaped shock where its outflow meets the thin interstellar gas ahead of it, like the wave that forms at the prow of a ship. Betelgeuse is more than a physical object. For many cultures, it has been a symbol in myth and story, associated with warriors, deities, and cosmic battles. Its bright red spark in the familiar shape of Orion has guided travelers and marked the seasons. Knowing that it will one day vanish in a final blaze adds a strange tenderness to its presence in the sky now. Even larger and stranger than Betelgeuse is a star that pushes the idea of big almost as far as we can imagine. VY Canis Majoris, a red hypergiant in the constellation of Canis Major. It lies roughly 3,900 light-years away, and it is one of the largest stars ever measured. Hypergiants are rare and unstable. They are far larger and more luminous than typical supergiants, and they burn through their fuel at a furious pace. VY Canis Majoris is thought to have a diameter that could be nearly 1,500 times that of the Sunday. If you placed it at the center of our solar system, its outer layers would stretch far beyond Jupiter's orbit, possibly out near Saturn's path. The numbers are so large that they become hard to feel. The mind almost slips as it tries to picture such a star. This vast size comes at a cost. Large, luminous stars live fast and die young. VY Canis Majoris has already entered a late bloated phase. Its outer layers loose and unstable. It is shedding mass at a remarkable rate, throwing off gas and dust that surround it in a complex, changing nebula. Observations show multiple arcs and clumps of material, each one a sign of past outbursts and irregular winds from the star's surface. Although its surface temperature is cooler than that of smaller blue-white stars, VY Canis Majoris is extraordinarily bright. It shines with a luminosity estimated to be hundreds of thousands of times greater than the sun's. Much of that light is absorbed and scattered by the surrounding dust, making it especially dramatic when viewed in infrared light. Eventually, this immense star will also reach the end of its life. The most likely outcome is a core collapse supernova, a titanic explosion that will outshine its host galaxy for a brief time and scatter heavy elements into space. Some researchers even suggest that a star this massive might, under the right conditions, collapse directly into a black hole with little visible explosion at all, its light snuffed out as its matter falls inward beyond the reach of view. By watching VY Canis Majoris, astronomers gain rare insight into what happens to the most massive stars as they approach their end. The star shows that hypergiants can be extremely unstable. with irregular patterns of mass loss and complex surface activity that ripple across their enormous, delicate atmospheres. Deep in the swollen atmosphere of VY Canis Majoris, astronomers think there are immense convective cells like the bubbling patterns on the sun's surface, but scaled up to almost unthinkable size. In those vast, slow-boiling regions, hot gas rises and cooler gas sinks, and sometimes the bubbling becomes so violent that great plumes of material are thrown off into space. Each eruption peels away a little more of the star's outer layers, feeding the thick nebula that now surrounds it. Within that nebula, the ejected gas cools and begins to change. In the shelter of dust and drifting clouds, atoms meet and join into more complex molecules. Radio telescopes have picked up the faint signatures of water vapor and carbon-based compounds in the outflow, hints that the star's breath has become a small chemical workshop. Dying giants like this help populate the galaxy with ingredients that will one day belong to new stars, new planets, and perhaps, far away in time, new living things. Modern imaging has revealed that the material around VY Canis Majoris is not a neat shell, but a tangled, lopsided cloud. Some regions are thick and bright, others thin and patchy. This unevenness suggests that the star does not shed its mass smoothly. Rotation, magnetic fields, and the chaotic motion of those giant convective cells all shape how and where the gas escapes. Each observation adds another brushstroke to the picture of how the most massive stars lose themselves to space. VY Canis Majoris stands in one of the last, most dramatic chapters of a giant star's life. Its slow unraveling is both violent and strangely beautiful. By watching it change, astronomers refine their understanding of how such rare giants evolve and how their deaths help sculpt galaxies, enriching them with heavy elements that will be recycled again and again. It is not alone in this role. Another red hypergiant, NML Cygni, hides in the rich star fields of Cygnus. It lives about 5,300 light-years away, in a region where many massive stars are born and die. NML Cygni is enormous, with a radius thought to be between roughly 1,100 and 1,600 times that of the Sunday. Yet, in visible light, it is strangely muted, its brilliance muffled by the very material it has thrown off. The star is wrapped in a thick shroud of gas and dust. Although it shines with a luminosity hundreds of thousands of times greater than the sun's, much of that light is absorbed by the surrounding cloud and re-emitted in infrared. Only by using infrared telescopes can astronomers truly glimpse its presence and begin to sketch its shape. Even there, the picture is complex. The shell around NML Cygni appears layered, built up by repeated pulses of mass loss over long spans of time. Within those layers, molecules such as water vapor and carbon monoxide linger in the cool, dense gas. The star is losing material at a rate thousands of times higher than the sun's gentle solar wind, peeling away its outer layers to build a personal nebula. The huge plumes and arcs traced in infrared and radio maps show that its atmosphere is anything but calm. Hypergiants like NML Cygni live in a constant state of flux, their outer regions rising, falling, and bursting outward under the push and pull of internal forces. At some point, all of this instability will reach a final limit. NML Cygni will likely end in a spectacular core collapse, exploding as a supernova, or perhaps slipping directly into a black hole. In either case, the enriched material it has, forged carbon, oxygen, silicon, iron, and more, will not be wasted. it will drift outward, mixing with interstellar clouds that will, one distant day, condense into new systems. In that way, massive stars are both destroyers and creators, seeding the galaxy with the raw materials of future worlds. The constellation of Cygnus itself is home to many high-mass stars, including the bright association known as Cygnus OB2, a cluster filled with luminous, short-lived suns. NML Cygni likely formed in such an active neighborhood alongside other giants that are now at different stages of their brief, brilliant lives. Studying its surroundings helps astronomers understand how groups of massive stars grow, influence one another, and ultimately disperse. Elsewhere in the sky, in the direction of Sagittarius, another giant tells its story in pulses rather than in shrouds. VX Sagittarii is a star roughly 5,000 light-years away that refuses to stay the same size. Its radius can swell and shrink between about 1,000 and 2,000 times the Sun's radius. As it expands, its outer layers cool, and the star appears redder and dimmer. When it contracts, the surface grows hotter and slightly brighter again. These changes do not follow a single, tidy rhythm. Instead, they weave together multiple cycles, overlapping and interfering, making the star's behavior hard to predict. Its brightness can shift by several magnitudes, so that it sometimes looks far fainter than we might expect for a star of such size. Deep inside, nuclear fusion and gravity are wrestling. Outward pressure from fusion sometimes wins for a while, pushing the star's layers outward. Then gravity reasserts itself, pulling them back in. The result is a slow, uneven breathing, a cosmic heartbeat that stretches over months and years. As VX Sagittarii expands and contracts, it also sheds material into space. Observations reveal clouds of gas and dust that were once part of the star, now floating in a thick envelope around it. In visible light, this dust can hide part of the star's glow. In infrared, where dust is more transparent, the full outline of its luminosity becomes clearer. Over time, the mass loss will strip away more and more of its outer layers. Someday, its core will no longer be able to support the weight above it. When the balance finally fails, VX Sagittarii will also collapse and explode, leaving behind a neutron star or a black hole, depending on how much mass remains. Some famous supernova progenitors, like Betelgeuse, show irregular pulsations in the years before they die. If VX Sagittarii is entering a similar phase, we may be watching the last great instabilities before its final transformation. But the exact timing of such an event is deeply uncertain. It could be soon in cosmic terms, or still many thousands of years away. By following its pulsations, astronomers test their models of stellar interiors, learning how energy moves through the deep, unstable layers of giant stars. Each irregular flicker provides information about the forces that drive and disturb these enormous suns. From these natural giants, it is a gentle step into a different kind of imagining. What might an intelligent civilization do with a star like VY Canis Majoris? A star of such scale represents an almost unimaginable source of energy. Physicist Freeman Dyson once suggested that a truly advanced civilization, a so-called Type 2 on the Kardashev scale, might one day surround its star with collectors to capture most or all of its light. For a hypergiant, the potential is staggering. VY Canis Majoris emits energy millions of times greater than the Sunday. Instead of a solid, rigid shell, which would be almost impossible to build and maintain, thinkers imagine a Dyson swarm, a loose, coordinated cloud of satellites, mirrors, and collectors orbiting at safe distances. Each piece would gather a small fraction of the star's output. Together, they could harvest an enormous amount of power. Such a swarm would have to orbit far enough away to avoid being destroyed by the star's intense radiation and violent outbursts. VY Canis Majoris is unstable and sheds material in unpredictable eruptions. Any structure placed too close would risk being battered by waves of gas and dust. The collectors would need to adjust their orbits over time, weaving around the star's changing wind like careful dancers. The materials for such a project would be immense in quantity. Entire asteroids, moons, and perhaps even planets might need to be dismantled and turned into thin shells, mirrors, and machines. Sophisticated manufacturing, perhaps involving self-replicating robots or advanced nanotechnology, would help build and maintain the countless pieces of the swarm. Then comes the question of what to do with the captured energy. One idea is to beam it using tightly focused microwaves or laser light to distant receiving stations, on planets, on habitats, floating in space, or on other structures scattered throughout the system. Another is to let storage satellites hold and distribute energy where and when it is needed, like reservoirs feeding a network of rivers. For us, these thoughts are more dream than plan, gentle exercises in imagining how far a civilization might someday reach. Yet they arise from the same quiet facts we see in tonight's giants. Stars swell, shed, pulse, and pour out vast amounts of energy, whether as the engines that enrich galaxies or as potential beacons for far-off minds. They sit in the dark and burn, writing slow stories in light. If some distant civilization truly could wrap a hypergiant star in a net of mirrors and collectors, its abilities would be far beyond anything we can currently build or even properly picture. This would be a society that no longer leans on fossil fuels or even on nuclear power, but draws instead from the raw brightness of its own star. Energy from a star like VY Canis Majoris could feed industries on many worlds at once, drive ships between stars, or even help shape artificial habitats and engineered planets. With power on that scale, they might be able to reshape climates, move planets to safer orbits, or gently nudge the lifetimes of their stars. Even though Dyson swarms and similar structures are still ideas on paper for us, astronomers have wondered whether someone else, somewhere, might already have built something like them. One way to look is to search for stars whose light seems oddly short of what it should be, or whose glow is strangely shifted toward infrared, as if a large share of their starlight were being absorbed and re-emitted as waste heat. A few stars have shown puzzling dimming patterns, such as the famous Tabby star, and some imagination has wandered toward artificial explanations. So far, though, every candidate has turned out to have more ordinary, natural possibilities, and there is no firm sign of a Dyson sphere anywhere. If a Dyson swarm ever encircled a star like VY Canis Majoris, it would almost certainly announce itself across great distances. The collected energy would have to go somewhere, most likely radiated away at lower temperatures, glowing in infrared like a vast warm shell. The same engineers might also be rearranging planets, carving stable habitable zones, or seeking ways to stretch the life of their star. Any of those changes could leave marks, unusual spectra, odd motions, or brightness patterns that do not match what we expect from normal stellar aging. There would be a limit, though. VY Canis Majoris is not a calm, long-lived star. It is already close to the end of its life and is expected to explode as a supernova on relatively short cosmic timescales. When that happens, the energy released in a few seconds will rival all the energy it has radiated in millions of years. A civilization that built the Dyson swarm there would have to plan for that ending, either abandoning the structure, letting it be destroyed, or somehow trying to channel even the explosion. Some dreamers have wondered whether an ultra-advanced society might one day be able to delay or soften a supernova, coaxing a star into a gentler death. For us, such things remain firmly in the realm of quiet speculation. Back in our own galaxy, there's a different sort of reminder of what massive stars become. In the soft glow of the Crab Nebula lies the Crab Pulsar, the tiny, dense heart left behind when a massive star exploded almost 1,000 years ago. In the year 1054 of the Common Era, people on Earth saw a new guest star flare in the sky, bright enough to be visible in daylight. It faded after many months, but the true remnant remained, a neutron star spinning in darkness. That remnant is only about 25 kilometers across, yet it holds more mass than our Sunday. Its matter is packed so tightly that a sugar cube-sized piece would weigh about 1 billion tons on Earth. As the original star collapsed, it shrank so drastically that it spun up, the way a figure skater spins faster when pulling in their arms. Today, the Crab Pulsar turns roughly 30 times each second, completing one spin in about 33 thousandths of a second. From its magnetic poles, it sends out beams of radiation like lighthouse beams. As the star spins, those beams sweep across space. When one of them crosses Earth, our instruments register a brief flash. The pulses arrive across many kinds of light radio: visible, X-ray, even gamma ray, making the Crab one of the brightest pulsars in the sky. The energy released by its rapid spin and intense magnetic field keeps the whole Crab Nebula glowing, feeding filaments and knots of gas with a steady stream of power. Over time, the pulsar's rotation slowly loses speed as it radiates away energy. Yet, every now and then, the Crab Pulsar glitches. Its spin suddenly jumps a little faster before settling into a new, slightly different rhythm. These tiny stumbles are thought to come from shifts in the star's crust and superfluid interior, places where physics behaves in ways we cannot reproduce on Earth. By timing these pulses with great precision, astronomers use the Crab Pulsar as a natural clock, testing ideas about gravity, space-time, and the behavior of matter under immense pressure. The pulsar also flings out high-energy particles, cosmic rays that race through space at nearly the speed of light. A small fraction of them eventually reach Earth, where they are counted by detectors as faint traces of events that began in the wreckage of that long-ago supernova. Space telescopes such as Hubble and Chandra have watched the Crab Pulsar in its nebula for years, tracking wisps and waves that ripple outward from the central engine. In the Crab we see, in real time, the afterlife of a massive star, not a silent ember, but a compact, restless engine. While red hypergiants like NML Cygni and VX Sagittarii dominate their surroundings through sheer size and light, the Crab Pulsar shows what follows after their final collapse: a small, dense object that still shapes its environment with invisible power. Even in death, a star can leave behind a legacy that continues to sculpt and illuminate the space around it. Far more distant, and on a scale even harder to hold in the mind, lies another kind of extreme remnant. Not a neutron star this time, but a black hole so massive that it anchors an entire, brilliant beacon. Ton 618 is what we call a quasar, a point-like, blazing source of energy, powered by a supermassive black hole at its center. Among known quasars, TON 618 stands out as one of the giants. Its central black hole is thought to have a mass of more than 40 billion suns. The light we see from TON 618 has been traveling for over 10 billion years. We are looking far back in time, to an era when the universe was young, galaxies were rapidly assembling, and central black holes were growing in great surges. That such a huge black hole could form so early remains a quiet puzzle. It pushes against our current ideas about how quickly black holes can grow by feeding on gas, dust, and stars. Like other quasars, TON 618 shines, not because the black hole itself glows, it does not, but because matter falling toward it forms a hot, swirling disk. As gas spirals inward, friction and compression heat it to tremendous temperatures, and it radiates across the spectrum from radio waves up through ultraviolet and X-rays. Around the quasar, fast-moving gas clouds emit bright spectral lines that let astronomers measure its distance and learn about its composition. The whole object is so luminous that it outshines the galaxy that hosts it. Compared to our own Milky Way's central black hole, Sagittarius A star, which has a mass of about 4 million suns, or even the enormous black hole in the galaxy M87, with a mass of about 6.5 billion suns, the black hole in TON 618 is on a different tier. To reach tens of billions of solar masses, it must have either grown with extraordinary efficiency or been born from a very massive seed. Perhaps the direct collapse of a huge primordial gas cloud or an early supermassive star. The quasar's power does more than simply shine. It can drive jets of charged particles at nearly the speed of light, piercing out of the galaxy's core for thousands of light years, and send winds that heat and stir the gas around it. In doing so, it can both quench and trigger star formation, shaping how the host galaxy grows. Quasars like TON 618 are thought to play a central role in the life stories of galaxies, acting as both engines and brakes in their evolution. The event horizon of a black hole, this massive, would be unimaginably large, its boundary spanning a distance that light would need days to cross. Yet to our eyes, TON 618 is just a point of brilliance. Far away, we infer the black hole's presence from the energy, the spectra, and the motions of surrounding matter. Studying objects like this helps physicists test their theories of gravity under extreme conditions and refine models of how structure formed in the early universe. If TON 618 can host such a monster, it is natural to wonder whether even larger black holes exist, hiding in the hearts of the most massive and distant galaxies, their light partially veiled by dust or distance. Each new observation nudges the limits of what we think is possible. From the dense heart of the Crab pulsar to the vast pull of TON 618, the universe keeps offering examples of extremes, tiny, spinning remnants, and sprawling invisible wells of gravity. And out there, in another massive galaxy, waits yet another giant black hole, Holmberg 15A, the gargantuan black hole anchoring a giant galaxy. Far out in the dark, there is a galaxy called Holmberg 15A, a soft blur of light in a cluster known as Abell 85, around 700 million light-years from here. At its heart sits one of the heaviest black holes we have ever inferred, a mass so vast it feels more like a quiet flaw in space than an object. The best estimates suggest it weighs at least 40 billion times as much as our Sun, an ultramassive anchor buried in an old, pale galaxy. Unlike the blazing quasars that shout across the universe, the black hole in Holmberg 15A is mostly hushed. It is not feeding on thick streams of gas right now, so there is no bright accretion disk, no roaring jets, only occasional flickers when some stray cloud or star wanders too close. Yet its gravity is always at work. It tugs on stars, gas, and even the dark matter that surrounds the galaxy, shaping the orbits of everything nearby. Holmberg 15A itself belongs to a special family called brightest cluster galaxies, the giants that sit at the centers of large galaxy clusters. They did not form in one quiet collapse. They grew by swallowing many smaller galaxies over billions of years. Each time two galaxies merged, their central black holes slowly spiraled toward one another and eventually combined, stepping up in mass. Over and over, this process likely built the monster now resting at Holmberg 15A's core. The galaxy's inner regions tell a story of that violent past. Instead of a dense, crowded core, Holmberg 15A has a surprisingly diffuse center with fewer stars than you might expect. When supermassive black holes merge, their combined gravity can fling nearby stars outward, a process sometimes called core scouring. The result is a gently hollowed-out heart where much of the central starlight has been scattered to larger orbits. Even from such a distance, we can weigh the invisible. By measuring how fast stars move near the center and how their motions change with distance, astronomers can infer the mass that must be hidden there. In Holmberg 15A, the speeds and patterns of those orbits point to a black hole far more massive than the ones in ordinary galaxies. There is little cold gas left in the core, no bright disk feeding it, which suggests that past mergers and outbursts may have stripped or heated away much of the available fuel. For now, the giant seems to be resting, having already reshaped its surroundings. Finding such a huge black hole in a relatively quiet galaxy nudges our sense of what is possible. It hints that there may be more ultramassive black holes than we once thought, some blazing as quasars in the early universe, others now sitting in calmer states like this, their active youth long past. Future observatories, especially those that can hear gravitational waves, may one day detect the echoes of the mergers that built them, ripples from ancient collisions written into the fabric of space-time. If Holmberg 15A shows us a giant that has settled into a kind of uneasy peace, another system, much farther away, reveals a black hole still in the middle of a stormy life. At the center of the Phoenix cluster, about 5.7 billion light-years from Earth, lives a supermassive black hole known as Phoenix A. Its mass may approach 100 billion times that of the Sun, placing it among the most massive candidates ever considered. Unlike the quiet heart of Holmberg 15, a Phoenix A is still feeding with astonishing appetite. As gas flows inward, Phoenix A blazes in X-rays and other high-energy light, making the cluster one of the brightest X-ray sources we know. In many galaxy clusters, such central black holes act like thermostats. Their outbursts heat the surrounding gas, keeping it too hot to cool and collapse into new stars. This feedback slows both star formation and further growth of the black hole. But in the Phoenix cluster, something different seems to be happening. Despite the intense energy pouring out of Phoenix A, the cluster is still forming stars at an unusually high rate. Hot gas in the core cools and condenses, feeding both new stars and the black hole itself. High-speed jets of charged particles shoot out along the black hole's poles, carving cavities in the cluster gas, yet they do not fully stop the cooling. It is as if the usual balance between heating and cooling has shifted, leaving a window where both rapid growth and vigorous star birth can occur together. Most supermassive black holes eventually slow their eating, partly because their own feedback chokes off the supply. Phoenix A, by contrast, appears to be in a phase of runaway growth, consuming matter and shining fiercely. Perhaps other clusters passed through similar phases earlier in cosmic history and have now faded into more regulated states. The Phoenix cluster may simply be catching one of these episodes in progress. Where all this leads is still an open question. If Phoenix A continues to feed at its current pace, it could eventually exhaust the cool gas in the cluster core, shutting down star formation and slipping into a quieter life more like Holmberg 15A. Or perhaps its environment, for reasons not yet clear, will continue to funnel gas inward, letting it grow even more massive than our current theories comfortably allow. Observations from X-ray telescopes such as Chandra and future high-energy missions are slowly filling in the details, showing us that not all black holes follow the same calm path toward old age. From these compact hearts of gravity, we can let our attention widen again to something even more sprawling, one of the largest galaxies we have ever found. IC 1101 is a giant elliptical galaxy about 1 billion light-years away, sitting at the center of the Abell 2029 cluster. Its size is staggering. Rough estimates suggest it stretches around 500,000 light-years across. For comparison, our Milky Way spans about 100,000 light-years. You could nestle our whole galaxy inside IC 1101 several times over and still have room at the edges. Unlike spiral galaxies with delicate arms and clear structure, IC 1101 is a smooth, diffuse glow, a vast cloud of stars without obvious patterns. Over billions of years, it has likely grown by absorbing many smaller galaxies, each merger puffing it out a little more and adding another layer of starlight to its wide halo. Those collisions scrambled any graceful spiral shapes that might once have existed, leaving behind a rounded, featureless form. The light from IC 1101 has a soft yellowish tint, the color of old stars. Young, blue stars live fast and die quickly, so their presence usually signals ongoing star formation. Here, their absence suggests that most of the gas that could make new stars has either been used up or heated and driven out. The galaxy is filled with ancient suns, long-lived and quieter, burning steadily while the universe ages around them. At its center, almost certainly, lies another enormous black hole with a mass measured in billions of suns. Even if it is not as extreme as TON 618 or Phoenix A, it still plays a central role, shaping the motions of nearby stars and any remaining gas. Like other massive galaxies, IC 1101 is also wrapped in a wide halo of dark matter. The visible stars alone cannot account for the speeds at which its outer regions move. Some unseen mass must be helping hold the galaxy together, extending far beyond the faint outer edges we can see. The number of stars inside IC 1101 is almost beyond counting. Estimates suggest it may hold on the order of 100 trillion stars, about 100 times more than the Milky Way. Its outer layers fade so gently into space that it is hard to tell exactly where the galaxy ends and the cluster's background begins. Some of the stars we see near its outskirts may in fact be drifting freely between galaxies, unbound wanderers that were flung out during long-ago encounters. Over time, as the universe continues to expand, galaxies drift farther apart, and the rate of mergers slowly declines. IC 1101 may still grow by consuming smaller neighbors within its cluster, but there will likely come a time when its growth slows and it settles as one of the great relics of an earlier, more crowded era. Looking at it is like looking at the possible fate of other big galaxies. Far in the future, when the Milky Way and Andromeda have merged into a single, larger elliptical, that distant descendant may share some of IC 1101's traits: an older population of stars, a powerful central black hole, and edges that dissolve softly into intergalactic space. Among such giants, there are others waiting in the dark, more vast ellipticals scattered through the nearby cosmos, like ESO 146-5, another enormous elliptical in our local universe, whose story continues this quiet journey through the universe's colossal structures. Closer to home in cosmic terms, there is another quiet giant, ESO 146-5, a massive elliptical galaxy in our broader neighborhood of the universe. It may not have the celebrity of the very largest known systems, but it is still enormous in its own right, weighing in at roughly 27 trillion times the mass of the Sunday in the region it inhabits. It dominates the gravitational landscape, a soft, rounded glow of ancient starlight. Like other large ellipticals, ESO 146-5 does not show graceful spiral arms or bright knots of newborn stars. Instead, it appears as a broad, diffuse cloud of older suns over billions of years. It likely grew through the steady merging of many smaller galaxies. Each collision blurred any previous structure, smoothing the system into its present rounded form and stretching its light far into the surrounding darkness. Its gentle yellow or reddish tint is the color of age. The hottest, shortest-lived blue stars have long since burned out, leaving behind cooler, longer-lived stars that shine with a softer light. Without a steady influx of fresh gas, new stars form only slowly, if at all. Many of the luminous giants that once populated the galaxy have already gone through their full life cycles, enriching the surrounding space with heavy elements. The visible part of ESO 146-5 is only part of its full extent. Faint, scattered stars drift far beyond the bright core, some likely torn from other galaxies during ancient encounters. These outer regions fade gradually into the background, making it hard to draw a sharp boundary between galaxy and intergalactic space. Beyond even that, an immense halo of dark matter is thought to surround the system, unseen yet crucial, providing the extra gravity needed to bind the whole structure together. Galaxies like this often sit near the centers of clusters, acting as anchors for smaller companions. Their huge mass curves space in their vicinity, drawing in lesser galaxies over long stretches of time. Some of those neighbors will eventually wander too close, be stretched by tides, and dissolve into the larger system. This slow form of galactic cannibalism helps ellipticals reach their tremendous sizes, one quiet merger after another. Although ESO 146-5 no longer blazes with new star birth, it is not frozen. Every star inside it is in motion, tracing its own path through the combined pull of billions of companions and the massive dark halo. Unlike spiral galaxies, where stars mostly follow orderly paths in a flattened disk, the orbits here are more chaotic and mixed, a record of turbulent encounters spread over eons. Our own Milky Way, with its spiral arms and bright nurseries of young stars, is still in a more active phase, but its long-term future may resemble galaxies like ESO 146-5. In a few billion years, the Milky Way is expected to collide with the Andromeda Galaxy. Over further billions of years, repeated interactions may reshape the merged system into a large elliptical, its spiral structure erased, its stars older, its light softer and more uniform. Nearby ellipticals provide a kind of time machine for astronomers. By studying galaxies like ESO 146-5 up close and comparing them to younger spirals far away, scientists can piece together how galaxies transform over cosmic time. Hot gas halos, visible in X-ray light, wrap many such giants, relics of past mergers and interactions that heated the intergalactic medium as materials settled into their deep gravitational wells. Even with its serene appearance, ESO 146-5 likely carries scars from a violent history. Faint streams of stars may still linger around it, tidal tails stretched out during past collisions. With sensitive instruments and careful image processing, astronomers sometimes tease out these ghostly features, each stream a whisper of a smaller galaxy that once drifted too near. Around it, swarms of globular clusters, dense, ancient gatherings of stars trace orbits like tiny satellites. Their numbers and distribution offer hints about how the galaxy grew. Some clusters may have formed in the galaxy itself. Others may be refugees from galaxies long since absorbed, surviving as compact relics of earlier times. Another nearby giant, Messier 87 in the Virgo cluster, shows a different face of the same story. M87 is a massive, elliptical galaxy, more than 120,000 light-years across, containing trillions of stars. At its center lies a supermassive black hole with a mass of about 6.5 billion suns, one of the most closely studied black holes in the sky. This black hole, often called M87 star, feeds from its surroundings, drawing in gas and sometimes stars that stray too near. As material spirals inward, it forms a hot accretion disk, glowing in X-rays and radio waves. One of the most striking sights in M87 is a long, narrow jet of high-energy particles that shoots out from the core. This jet extends for thousands of light-years, moving at nearly the speed of light, guided by intense magnetic fields around the black hole. Even modest telescopes can glimpse the jet as a faint streak emerging from the galaxy's center. Its light does not come from nuclear fusion, like a star's, but from charged particles accelerated along twisted magnetic field lines. Watching this jet has helped astronomers understand how black holes can influence their surroundings on scales far larger than the event horizon itself. In the year 2019, M87 star became famous when the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow. Using radio observatories spread across Earth, they created a planet-sized virtual telescope and captured a glowing ring of gas encircling a dark central region. That shadow marks where light itself can no longer escape. The image matched predictions from general relativity, turning decades of theory into something we could finally see. The stars near M87's core move at astonishing speeds under the grip of the central black hole's gravity. By measuring their motions, astronomers can refine their estimates of the black hole's mass. Beyond the bright heart, M87's outer halo contains vast numbers of globular clusters, some more than 10 billion years old. These clusters, along with the hot X-ray glowing gas that fills the Virgo cluster, speak of a long history of mergers, stripping, and interactions. While galaxies like ESO 146-5 and M87 show us mature giants and their powerful hearts, the motions of galaxies on much larger scales point to something even more mysterious. Our Milky Way, together with the Andromeda Galaxy, the Virgo cluster, and many other systems, is moving through space toward an unseen region. This drift is not just the usual expansion of the universe. It is a motion superimposed on that expansion, drawn by an enormous, hidden concentration of mass. Astronomers call this mysterious pull the Great Attractor. It is not a single object, but a broad region of space whose combined gravity influences entire clusters of galaxies. It lies roughly 150 to 250 million light-years away in the direction of the Centaurus and Norma constellations. Estimates suggest that the total mass in this area may be equivalent to tens of thousands of large galaxies, making it one of the most significant gravitational features in our cosmic neighborhood. The Great Attractor was first suspected in the 1970s and 1980s, when careful maps of galaxy motions showed that many systems, including our own, were drifting toward the same general region at high speeds. The known clusters and galaxies nearby were not enough to explain this flow. Something more massive and largely hidden had to be contributing. Part of the difficulty in studying the Great Attractor is that it lies behind the dense band of the Milky Way. This part of the sky, called the zone of avoidance, is crowded with stars, gas, and dust that block our view in visible light. Astronomers have had to rely on other wavelengths, such as radio and X-rays, to peer through this veil. Early ideas suggested that the Great Attractor might simply be a particularly large supercluster of galaxies, but later observations showed a more complicated picture. The mass in that region does not appear as one single, obvious clump. While there are many galaxies and clusters, they do not seem to account for the full gravitational tug we measure. This has led to the thought that dark matter may play a major role, its invisible presence adding to the pull. If there is a high concentration of dark matter in and around the Great Attractor region, it could explain why galaxies are being drawn that way without a single bright structure giving itself away. As maps of the universe improved, astronomers realized that the Great Attractor itself is part of an even larger structure, the Laniakea supercluster, whose name means immense heaven. Laniakea gathers together many clusters, including Virgo and others, over a region roughly 500 million light-years across. Within this vast web, the Great Attractor seems to be one of the central gravitational focal points, helping to direct the flow of galaxies. The motion of galaxies there is not a simple straight-line fall. Their paths are also tugged by other massive concentrations nearby, including the Shapley supercluster, an even larger and denser assembly of galaxies beyond the Great Attractor. Some studies suggest that while galaxies are currently moving toward the region of the Great Attractor, the overall flow of structures in that part of the cosmos may be bending toward Shapley, which could be an even more dominant source of gravitational pull. On these vast scales, the Great Attractor becomes less a single thing and more a reminder of how gravity quietly arranges the universe. Galaxies are not scattered at random. They gather into filaments and nodes, linked in a delicate cosmic web with great empty voids between them. The region we call the Great Attractor marks one of the stronger knots in that web, a deep hollow in space where mass is pooled so thickly that whole clusters of galaxies feel its pull. Here at home, Earth circles the Sun at about 30 kilometers per second. The Sun, in turn, orbits the center of the Milky Way at roughly 220 kilometers per second. But when astronomers look at how our whole galaxy moves against the broader background, they find another layer of motion. The Milky Way, along with its neighbors, is drifting toward the region of the Great Attractor at something like 600 kilometers per second. Every star you have ever seen, every quiet world we know, is part of that slow, grand fall, wrapped into a motion we cannot feel. There is no need to worry. These shifts happen over billions of years, and the universe itself is expanding at the same time. Dark energy, the mysterious pressure that drives that expansion to accelerate, stretches space between clusters and superclusters. Its influence counteracts the pull of massive structures, preventing everything from simply collapsing into a single, crowded heap. Our path through the cosmos is a compromise between falling inward and being carried outward. As instruments improve, so does our view of the hidden regions near the Great Attractor. Infrared and radio telescopes can peer through the thick star fields and dust of the Milky Way, mapping galaxies that are invisible in ordinary light. By tracing their motions with greater precision, astronomers hope to untangle exactly how mass is arranged there, and how that arrangement steers the flow of galaxies on the largest scales. Closer, and much more visually dramatic, another kind of gravity dance is playing out in the Antennae galaxies. About 45 million light-years away in the constellation Corvus, two galaxies NGC 4038 and NGC 4039 are in the midst of a long, slow collision. Together, they form a tangled shape that, in deep images, sprouts two long, sweeping arcs of stars and gas. Those arcs resemble the delicate antennae of an insect, which is how the pair got its name. Their encounter is not a single, sudden crash, but a drawn-out embrace that will last hundreds of millions of years. As the galaxies pass through each other, their vast clouds of gas and dust are tugged and pulled, flung out into curving tidal tails. Stars themselves almost never collide. There is simply too much empty space between them, but their orbits are twisted and stretched by the changing gravitational field. The real collisions happen in the interstellar medium, where gas clouds slam together, compress, and collapse. In the Antennae, this has set off a storm of new star birth. Whole regions glow with the light of young, massive stars that have only just ignited. Thousands of bright, compact star clusters speckle the scene, some of which may survive as globular clusters long after the merger has settled into a single new galaxy. The most massive young stars will live fast and die violently, exploding as supernovae and stirring the surrounding gas with heavy elements that will one day be folded into new stars and planets. By looking at the antennae and different kinds of light, astronomers can trace different layers of this transformation. Infrared observations reveal star-forming regions still wrapped in dust cocoons. X-ray images show pockets of superheated gas and the remnants of recent explosions. Radio maps highlight the cold gas reservoirs that may fuel the next wave of star formation. Taken together, they offer a time-lapse of galaxies in the act of becoming something new. In a quiet way, the antennae offer a glimpse of our own distant story. The Milky Way and the Andromeda Galaxy are on course to meet in a few billion years. Their dance will unfold in slow motion, with repeated close passes before their disks finally merge into a larger, more rounded system. Our Sun and its planets are unlikely to collide with anything directly, but their orbits may be reshaped. Some stars will be flung into intergalactic space, others drawn closer to the new common center. Most large galaxies, including both the Milky Way and Andromeda, shelter supermassive black holes in their cores. When their host galaxies merge, those central black holes sink toward each other, forming a binary that tightens over time as it interacts with surrounding stars and gas. In some cases, the pair eventually collides, releasing a sharp burst of gravitational waves, ripples in space-time that wash across the universe. The antennae have not yet reached that stage, but their chaotic heart hints at the complex gravitational story still to come. From this intimate collision of two galaxies, we can widen our view again to something much larger, a whole cluster of galaxies bound together. The Coma cluster, about 320 million light-years away, in the constellation Coma Berenices, is one of the best studied examples. It contains more than 1,000 large galaxies and many thousands of smaller ones, all orbiting within a shared halo of dark matter and hot gas. Within Coma, galaxies of many kinds coexist. Some are spirals resembling the Milky Way. Others are smooth ellipticals, their star formation long since faded. There are also irregular systems whose shapes have been distorted by past encounters. As galaxies plunge through the cluster's environment, they feel a wind of hot plasma blowing past them. That plasma, heated to tens of millions of degrees, can strip away the gas that galaxies need to make new stars, a process sometimes called ram pressure stripping. Two particularly massive ellipticals, NGC 4889 and NGC 4874, sit near the cluster's center like twin anchors. Each hosts a supermassive black hole, billions of times the Sun's mass. Over billions of years, they have grown by merging with other galaxies, swallowing their stars and drawing in their dark matter halos. Around them, hundreds of lesser galaxies orbit in a long, slow ballet. The space between Coma's galaxies is filled with that hot, X-ray emitting gas. Observations from telescopes like Chandra and XM, M. Newton, have mapped this glow, revealing the distribution of gas and, indirectly, of dark matter. Without a deep gravitational well, the gas would drift away. Its confinement tells us that there is far more mass in the cluster than what we see in the stars alone. Coma was one of the first places where this hidden mass, what we now call dark matter, became hard to ignore. In quieter environments, a galaxy can go on forming stars from slowly cooling gas for eons. Inside a rich cluster like Coma, life is harsher. Many galaxies have had their gas stripped, leaving them with aging, red stellar populations and little fuel for future generations. It is one reason why clusters tend to be filled with older, redder ellipticals rather than blue, star-forming spirals. Coma is not an island either. It belongs to the Coma supercluster, which in turn is woven into the larger cosmic web. Between clusters like Coma, vast voids stretch out regions where galaxies are scarce and space is almost empty for millions of light years. Our local group, with the Milky Way, Andromeda, the Triangulum Galaxy, and a crowd of smaller companions, is a much smaller gathering, but over immense spans of time, groups like ours can fall together, merging into larger clusters in a process that mirrors Coma's own history. Radio observations in the Coma cluster have revealed great arcs and halos of emission, signs of jets and outflows from supermassive black holes interacting with the intracluster gas. These jets carve cavities, stir turbulence, and help keep the gas hot. In this way, black holes that are tiny compared to the cluster as a whole can still shape its internal weather. Standing back, the Coma cluster becomes one bright knot in the cosmic web, a place where gravity and dark matter have drawn galaxies, gas, and black holes together. It is a reminder that the universe is structured on many levels: stars in galaxies, galaxies in clusters, clusters in superclusters, and between them all, the wide, dark expanses that we call voids. Among them, a vast one, known as the Boötis Void, an immense abyss in the cosmic web. On the largest scales, the universe looks less like a random scatter of lights and more like a delicate lacework. Galaxies gather along long, thin filaments, strung together like beads. while in between those strands lie enormous regions where almost nothing seems to live. One of the most striking of these hollows is the Boötes Void, a place where the usual glitter of galaxies falls almost completely away. The Boötes Void sits roughly 700 million light-years from us. It stretches for about 330 million light-years from one side to the other, a dark bubble in the cosmic web. If you place the Milky Way at its center and sent a beam of light toward the nearest normal galaxy, that light would need more than 100 million years just to arrive. Compared to rich clusters like Coma or Virgo, where thousands of galaxies crowd into a much smaller region, the emptiness of the Boötes Void feels almost unsettling. When astronomers first mapped it in the early 1980s, they expected to find tens of thousands of galaxies scattered throughout such a huge volume. Instead, careful surveys turned up only a few dozen, sprinkled sparsely across the darkness. It was as if a piece of the universe had been scooped out and left unfinished. That mystery led to gentle questions. How does a void like this appear? And what story does it tell about how the universe grew? The answer seems to lie in the universe's earliest wrinkles. Right after the Big Bang, matter was not perfectly smooth. Some regions were a little denser, others a little thinner. Over billions of years, gravity pulled matter from the underdense areas toward the denser ones. The rich regions collapsed into galaxies, clusters, and superclusters, while the poor regions were slowly drained. Voids like Boötes are the leftovers of those less dense patches, places that became even emptier as time passed and galaxies migrated outward along the filaments. Even so, void does not mean perfectly empty. A few galaxies linger inside the Boötes Void, clinging to faint threads of the cosmic web. Some of them line up in a fragile, string-like arrangement, a hint that even in these great hollows, structure still exists, but their environment is profoundly different from that of galaxies in crowded clusters. They drift in isolation, almost untouched by the close encounters, mergers, and tidal tugs that constantly reshape galaxies in denser regions. That solitude may change their lives. Without neighbors to strip away their gas or stir their disks, void galaxies might hold on to more of their original material. They may form stars more slowly or in bursts, following growth patterns that differ from galaxies in busy neighborhoods. By studying these loners, astronomers hope to understand how much of a galaxy's evolution is written by its surroundings and how much unfolds from within. The Boötes Void is one of the largest known, but it is not alone. The universe is full of such hollows, large and small, like bubbles in cosmic foam. Galaxies live on the thin walls between them, in filaments and sheets that lace together into something that looks almost organic. These empty regions are not just curiosities. They help define the shape of the universe and offer subtle clues about its invisible components. In voids, normal matter is scarce, and dark matter is thought to be more diffuse as well. Dark energy, the mysterious influence driving the accelerated expansion of the universe, may play a larger relative role there, gently pulling everything apart. By measuring how voids expand, how galaxies move around their edges, and how light is bent as it passes through them, scientists learn more about the balance between dark matter and dark energy that governs the cosmos. If voids show us where matter is missing, structures like the Sloan Great Wall show us where it has gathered in spectacular abundance. The Sloan Great Wall is a colossal filament of galaxies discovered in the early 2000s during the Sloan Digital Sky Survey. It stretches for roughly 1.38 billion light-years, a chain of clusters and superclusters linked by threads of galaxies and dark matter. Light, even at its incredible speed, would need more than 1 billion years to travel from one end to the other. This wall is not a solid barrier, just a region where matter has pooled more richly than average. Within it, galaxies clump into dense knots connected by thinner bridges. The Milky Way, which is about 100,000 light-years wide, would be a tiny fleck against such a structure. The Sloan Great Wall spans more than 13,000 times our galaxy's diameter, an expanse so large that language begins to feel small beside it. Structures like this gently challenge one of the simplifying ideas of cosmology, that on the very largest scales, the universe should look roughly the same everywhere, with matter smoothly averaged out. The cosmological principle says that if you zoom out far enough, local lumps disappear into a uniform mist. Yet the Sloan Great Wall presses against the expected size limits of what gravity should have had time to assemble in a universe 13.8 billion years old. Its existence hints that either our models of growth are still missing some details, or that these enormous features sit right at the edge of what is just barely possible. Inside the wall, galaxies and clusters are not frozen in place. They orbit, fall together, and sometimes merge, even as the expansion of the universe stretches the space between them. Gravity tries to pull the structure tighter. Cosmic expansion slowly pulls it thinner. Over enormous spans of time, some parts of the wall may grow denser as clusters coalesce, while others drift apart and fade, dissolving into smaller, disconnected pieces. By mapping the positions and motions of the galaxies in and around the Sloan Great Wall, astronomers trace the hidden scaffolding of dark matter that underlies it. Galaxies are like lanterns hung along an invisible frame. Their distribution tells us how dark matter is arranged, and how the universe has evolved from the nearly uniform glow of its earliest moments into the richly textured web we see now. It is worth remembering that the Sloan Digital Sky Survey, which revealed this structure, mapped only a slice of the sky. Much of the universe remains uncharted in similar detail. Larger, even stranger structures may lie beyond our current reach, waiting patiently until our instruments become sensitive enough to find them. All of this, the voids and walls, clusters and filaments, lives within a region we call the observable universe. That phrase sounds grand and complete, but it is really a careful admission of limits. The observable universe is simply the part of all that exists from which light has had time to reach us since the beginning of cosmic expansion. It is less a solid edge than a horizon, shaped by the finite speed of light and the finite age of the cosmos. When we look at a distant galaxy, we see it not as it is now, but as it was when its light began the journey toward us. The farther away we look, the further back in time we peer. The most distant objects we can currently observe are sending us light that has been traveling for about 13.8 billion years, roughly the age of the universe. Yet because space has been stretching as that light travels, those objects are now much farther away than that travel time suggests. If we could somehow pause the expansion and measure the distance to the farthest galaxies whose light reaches us today, we would find that they are about 46 billion light-years away in every direction. That makes the diameter of our observable universe about 93 billion light-years. It is a sphere centered on us, not because we are special, but because every observer anywhere in the cosmos has their own horizon, defined by how far light can have traveled to them since the beginning. Charting this immense region is more complicated than drawing a map of land and sea. Space is expanding, galaxies are moving, and light itself is stretched as it travels, shifting toward the red end of the spectrum. For nearby stars and galaxies, astronomers can sometimes use parallax, watching how an object's apparent position shifts as Earth moves around the Sun to estimate distance. Farther out, they rely on standard candles, like certain types of supernovae, and on redshift, the amount by which a galaxy's light has been stretched by the expansion of space. Combining these measurements, they build three-dimensional maps that show not just where galaxies are, but when we are seeing them. On those maps, the cosmic web emerges again: clusters, filaments, walls, and voids, stretching to the edge of what we can see. Beyond the realm of galaxies lies an even older light, the cosmic microwave background, a faint glow that fills the sky in every direction. It is the afterglow of the early universe, released when the cosmos was young and hot, and then stretched and cooled over billions of years. The cosmic microwave background marks a practical limit to our vision. Before that time, the universe was so dense and energetic that light could not travel freely. It was constantly scattered by particles in a glowing fog. We can model those earlier moments with physics and mathematics, but we can never receive direct light from them. In that sense, the cosmic microwave background is a kind of inner horizon, the oldest light we can ever hope to see. Beyond our outer horizon, there is almost certainly more, perhaps an infinite expanse of galaxies, clusters, walls, and voids, much like the ones we know, perhaps something stranger. But the expansion of space means that some regions are receding from us faster than light can bridge the growing gap. Their signals will never arrive. They are not breaking any rules. General relativity allows space itself to stretch this way. It is simply that those parts of the universe have slipped over a line beyond which they can no longer share light or information with us. In that sense, our observable universe is like a softly lit island in a much larger night. We can measure its size, map its structure, and trace its history back to its earliest visible glow, but we cannot see past its shores. New observatories, like the Vera Rubin Observatory, with its deep, wide surveys of the sky, will sharpen our maps and reveal fainter, more distant galaxies. They will not push the cosmic horizon outward. That boundary is set by time itself, but they will let us fill in more detail within it. Beyond that softly lit horizon, there is more universe than we will ever be able to see, not because it is hidden behind clouds or dust, but because light itself has not had enough time to cross the distance. The cosmic horizon is a quiet rule written by two simple facts. The universe has a finite age, and light moves at a finite speed. Anything beyond a certain distance has not yet had the chance to send us its story. As space continues to expand, that horizon is not fixed. Regions that are just barely within reach now will, over immense spans of time, slip away. Their light will stretch, fade, and eventually never quite make it to us. In that sense, new parts of the cosmos are always drifting out of touch, even as we build better telescopes to see more clearly within the shell we already have. Yet everything we do see suggests that the universe continues beyond our limits in a smooth, unbroken way. The cosmic microwave background, that faint afterglow from the early universe, looks almost the same in every direction. The patterns of galaxies and clusters near the edge of our observable sphere do not suddenly end or curl. If there were a sharp edge to space itself, we would expect odd distortions, abrupt cutoffs, places where the tapestry simply stopped. Instead, The data whispers a different story. Whatever lies beyond seems to follow the same broad rules. There are a few possibilities, and each is strange in its own gentle way. One is that the universe is truly infinite, stretching forever, with uncountable galaxies scattered through an endless volume. In that case, our observable patch is just a tiny circular window on an unimaginably large wall. Another possibility is that the universe is finite but unbounded, like the surface of a sphere is finite but has no edges. If space has such a shape and more dimensions than we can picture, you could, in principle, travel in one direction long enough and eventually return to where you started, never crossing a border, only looping around. The whole of everything would be limited in size, yet still without walls. Some theories go further and suggest that the physics itself might vary beyond our horizon. Here, in our observable region, the constants of nature, things like the strength of gravity and the charges of particles, seem the same wherever we look. But in some models, the wider cosmos could be divided into domains, each with its own version of these constants, its own settings. In one domain, gravity might be a little stronger. In another, dark energy might dominate even more completely. Galaxies there might form differently, or not at all. Beyond that, there is the more speculative idea of a multiverse, not just distant regions of the same space, but entirely separate universes, disconnected from ours, except in mathematics and imagination. They might bubble off from high-energy events or arise from quantum fluctuations in some deeper underlying reality. Each one could have its own blend of particles, forces, and cosmic histories. In most of them, conditions might never permit stars or life. In a few, perhaps, they might. For now, this remains a quiet thought experiment. We have no direct evidence that such other universes exist. Even within our own universe, the future holds more separation. Dark energy is driving an accelerated expansion, so that distant galaxies are not only receding from us, they are doing so faster and faster. In the far future, many of the galaxies we can see today will cross a kind of one-way line. Their light, stretched and weakened by the expanding space between us, will never arrive. Our observable region will become, in a relative sense, smaller and lonelier. What dark energy will do over truly cosmic times is still uncertain. Some models imagine it growing stronger, tearing galaxies apart, then stars, and finally atoms themselves in a scenario called the Big Rip. In that case, far beyond our current horizon might already be a realm of ever more violent stretching, where structures are being unmade. Other models picture dark energy fading, letting gravity slow the expansion and, in some distant era, possibly even reverse it. Then, isolated regions could begin to fall back together. We do not yet know which path our universe is following. There is a philosophical hush at the edge of all this. If something lies forever beyond our power to observe, in light or in any other signal, does it matter in a practical sense? Some scientists say that only the observable universe is physically meaningful because only it can ever influence us. Others feel that the unobservable parts are just as real, even if they never touch our detectors. The universe does not adjust itself for our instruments. It simply is, whether or not we can see all of it. Once, people wondered if the world itself had an edge, if ships might fall off the rim of the sea. Later, astronomers debated whether the stars were fixed on a shell or whether they extended into a deeper darkness. Now we know that the stars are suns, that galaxies are islands of suns, and that those islands are woven into something far larger. And still, we arrive at another limit. Not the edge of the world this time, but the edge of what light can tell us. To understand even the part we can see, we need more than telescopes. The universe changes too slowly to watch whole galaxies evolve, and its structures are too complex to capture with a single neat equation. So we build something else. Numerical universes grown inside supercomputers. These machines, capable of performing trillions of calculations per second, let us compress billions of years into weeks or months of computation, watching digital cosmoses unfold from simple beginnings. In one famous project, called the Millennium Simulation, researchers fed in what we know about the early universe and the laws of gravity, then let dark matter particles, billions of them, in the code pull on one another. Slowly, in the memory of the machine, a cosmic web emerged. Filaments thickened, clusters formed at their intersections, and vast voids opened between them. No stars were modeled directly, only the invisible scaffold of dark matter. Yet the result, when compared to real galaxy surveys, looked strikingly familiar. It was as if we had grown a miniature universe in silico, just to see what shapes gravity prefers. Later projects went further. The illustrious simulation began only a short time after the Big Bang, when the universe was still young, and followed it to the present day. It added ordinary matter to the recipe, gas that could cool, condense, ignite as stars, and be blown back out by supernovae. It included black holes that could form in galactic centers, feed, and send energy back into their surroundings. In that digital universe, galaxies spun themselves into spirals, collided, merged, and grew. Heavy elements spread outward from dying stars, seeding space for the next generation. Another suite of simulations, called EAGLE, focused more closely on the lives of individual galaxies and their environments. It tried to capture the delicate balance between star birth and feedback, how exploding stars enrich and heat the gas around them, and how supermassive black holes can either quench or stimulate further growth. The galaxies that emerged from these runs looked, in many ways, like the ones we see through telescopes. Similar masses, similar shapes, similar patterns of clustering. Setting up these simulations is a careful act. Scientists must choose initial conditions that match what we infer from the cosmic microwave background: tiny ripples in density, certain ratios of dark matter to ordinary matter, a specific overall expansion rate. They then write down the fundamental equations: gravity, fluid dynamics, thermonuclear reactions, and ask the computer to apply them step after step, over and over, as virtual time flows forward. Even on some of the fastest machines on Earth, a single, detailed run can take weeks or months to complete. When the results match what we observe, when the simulated galaxies align in their properties with real ones, when the large-scale patterns of filaments and voids line up with surveys, it is a quiet reassurance that our understanding of cosmic physics is not entirely misguided. When the simulations fail, they point the way toward missing ingredients or mistaken assumptions. They have helped us estimate how much dark matter must exist and how dark energy guides the universe's expansion. Supercomputers also let us explore more extreme corners of the cosmos. By numerically solving Einstein's equations for curved spacetime, researchers can watch what happens when two black holes spiral together and merge. Long before the first gravitational waves were detected on Earth, simulations predicted the detailed patterns those ripples in spacetime should carry. When observatories like LIGO finally heard those faint chirps, their shapes matched the simulated signals with eerie precision. On smaller scales, collision simulations show how galaxy encounters twist disks into tidal tails, trigger waves of star formation, and sometimes leave behind smooth ellipticals where spirals once spun. Early universe simulations test ideas about cosmic inflation, that brief burst of rapid expansion thought to have stretched quantum fluctuations into the seeds of all later structure. Beyond pure research, these digital universes have become a way for people to feel the cosmos more directly. Software like Space Engine or Universe Sandbox uses real astronomical data and physical models to let anyone fly through virtual galaxies, drift above exoplanets, or watch two star clusters merge in slow motion. With a headset on, you can stand on a simulated Mars, glide through Saturn's rings, or float at the edge of a glowing nebula. Planetariums and museums use such visualizations to turn raw numbers into journeys that the mind and heart can follow. As computing power grows, new generations of simulations projects with names like TNG-50 and beyond track gas clouds, star clusters, and black holes in ever finer detail. Some will begin to toy with more exotic physics, exploring what might happen if certain assumptions about dark matter or dark energy are changed. None of these models can ever be perfect copies of reality. They are sketches, not photographs, but they are detailed sketches guided by observation that let us test ideas we could never try in a laboratory. We live on a small world, orbiting an ordinary star inside one galaxy among trillions. Around us stretches a web of clusters and voids, walls and hollows, black holes and quiet dwarfs, all governed by a handful of deep laws. Much of it we will never see. Much of it we can only glimpse through light that has traveled for billions of years, or through patterns in simulated universes inside humming machines. And yet, here you are, listening at the edge of sleep, holding all of this in your mind for a little while. Horizons and walls, voids and waves, the known and the forever unseen. The universe is vast, but your awareness of it is intimate and small and gentle. That, too, is a kind of miracle.